And finally, we can blame someone else for issues, right?
Yeah,
Probably you can resolve the name. It's not BGP.
that's right.
Hey, we're
Hey,
like
greetings, fellow nerds. Welcome to another episode of Between Two Nerds, where we talk with prominent guests about all aspects of the networking industry, from protocols old and new, including DNS that we were just talking about, to industry trends and drivers, to up and coming technologies, and as always, things you should know to further your career. And we've got Peter back with us today. Thanks, Peter, for joining us once again. We're just going to make you a permanent guest on this show.
Thank you.
And maybe we'll promote you to host one of these days.
and you'll have to change your name to Jeff, obviously, but that's
yeah, that's right. That's right.
That's the easy part.
we actually have had shows in the past where our guest Jeff Haas was on, and so we had a
oh, that's okay. Jeff Haas. Oh yeah, that's
so we were the
fitting.
three Jeffs for that. But anyway, Jeff, you want to talk about where we're going? We've been talking about AI ML infrastructure. We sort of started, and we've had Peter guiding us through all of this. We sort of started with what are the specific demands around AI ML workflows, and then from there started talking about the specific requirements for infrastructures to support those workflows. And I think that's kind of where we left off last time. I know, Peter, I think you gave us kind of a history of where we are to today. So Jeff, are we talking more about that topic of kind of just picking up with today, right?
Yeah, I think we are kind of progressing in hierarchy of Maslow. We go from infrastructure to application, and communication library and the traffic patterns related sit exactly in between of BGP or your routing protocol of choice, and how you build your fabric, and really learning training. So I think this would be a good discussion for this meeting. We've got a couple of slides. And I think we'll start with that.
Just to interrupt, you mentioned communications libraries. I honestly can't remember. I think we've talked about it in passing, but we haven't really ever talked in detail about Nickel, have we?
No, and maybe that's kind of good discussion for one of the upcoming.
Yeah.
Nickel stands for NVIDIA, so it's very close to our hearts. And
yeah, I mean, it's NVIDIA, but it's pretty much, it seems like almost anybody running an ML infrastructure these days has to understand Nickel, because because if you're doing that infrastructure at any scale, you're probably running NVIDIA servers, and if you're running NVIDIA servers, you've got to understand Nickel.
Absolutely.
Yeah. So anyway, sorry, I interrupted.
And that's the communication library, so I'll kick off and leave it to Peter to talk. So
communication library?
Oh, there it is.
All right.
Yeah.
Okay.
So if you happen to run more than one GPU, you need to connect them. And jobs are collective. So we assume that there's more than one GPU that need to communicate with other GPUs. And there are different types of network between them, from PCIe and NVLink on the single node up to network that we have mostly been focused on. And Nickel is a communication library developed by NVIDIA to connect all the things. And it could be as small as a few devices sitting on PCIe up to hundreds of thousands GPUs sitting in 1 gigawatt data center. Nickel is open source, so it can be downloaded from GitHub, source codes on GitHub, and there's significant amount of information available on NVIDIA, and the code as well, documented, very readable, C++ code. So we talked about single GPU. This is not really of interest for the discussion, so we're going to move to parallelization, where we use more than one GPU, more than one server, and Peter will take it from here.
Oh, thanks, Jeff. I always get the take it from here part. While Jeff is trying to multitask between his meetings at the workplace. Where do we begin? So Jeff briefly mentioned parallelization as, of course, the key that drives network scaling. And that is probably a very prominent fact about training neural networks, because that's what made possible everything, every advancement we have recently in network fabrics. Again, some echo. Is it gone? Okay. Let's look at briefly at previous slide, Jeff, just real brief, because it's good to show how things work differently, right? The previous slide was showing one GPU, right? If you look at the previous one, you have a model which is a bunch of numbers, right? Of course, it sounds a bit diminishing, but it is a collection of parameters and other attributes. There's also additional things you store in memory. You would have gradients, you would have optimizer states, you have activations in transit, and so on. But the whole idea is that a single GPU in the beginning of the good old days would store the full model. And when you do forward pass computation for the model, you do multiplications, you get the vectors, and you feed them through the network layers forward, right? You get the result, you calculate the error, and propagate it back. It sounds utterly simplistic, and funny enough that principle of using backpropagation hasn't changed since, like, I think the invention, maybe it was early 80s, late 70s, I forgot the exact date, when people invented backpropagation as a method to train neural networks. The important part is that you have parallel execution here as well. Like, what made GPUs so successful is the massive parallelism, where you have thousands of threads that can perform multiplications efficiently. And I think we briefly mentioned in the past that the industry tried to mimic that compute intensity by trying to build optimized ASICs for multiplications, right? Like a TPU did, and the other companies. GPU architecture, however, left more flexible in that regard. Always multiple cores aren't designed just for multimoles. They can do many other things within the architectural limits, of course. But that was the driver. Like, for the first N years of deep learning, you would train your model like Alex at ResNet on a single GPU, right? So you would just take a batch of data, feed it through, and then update the error. And even back then was the interesting part, right? You had, let's say, 1 million images or 1 million samples of something. Maybe it's too much, whatever. But when you feed the data from a network, you feed a small batch, a subset of it. Because conceptually, to make error prediction accurate, you have to feed everything in once and then apply the error from all the samples. But that was computationally unfeasible, right? So people would feed mini batches and apply the error from every mini batch to the network. And that naturally led to the idea of, on the next slide, make things data parallel, which was probably the most obvious and most evident way to scale the training. When you take the same model, exactly, all the weights, all the gradients and states, and you copy them across multiple GPUs. It could be on one server. In the good old days, you would maybe have GPUs on video cards, on PCIe cards, multiples of them, but they all have the same model or replica. But the difference is that here you feed different subsets of data. If you have 1 million examples, million samples of data, you get, let's say, 10 images, different images, and feed them to different GPUs, right? And they all get different results in the end, slightly different error rates, right? And then you try to apply the corrections, right? The gradient by propagation, but instead of applying locally, you exchange gradients to average the value, right? So as opposed to working individually, right, on this problem, now every GPU applies its local batch, calculates the error, and then exchanges the correction factors, the gradients. And the number of gradients will be proportional to the number of parameters, right? Because you have to apply the adjustment to every parameter of the network. So if you have, let's say, a model which is 1 billion parameters, you have to have 1 billion gradients exchanged eventually, right? The good thing is that you don't have to exchange them in one shot. As you do backpropagation, typically you do some level of grouping and you exchange gradients as you go backwards layer by layer. And that allows you to do various tricks, such as overlap compute of one layer in backpropagation with the communication of previous layer, right? That was, I think, the key for very fast and efficient so-called strong scaling in the early days. Strong scaling means you keep the data set the same, so the batch size the same, but you add more GPUs, right? But they all get about the same number of samples. The problem with strong scaling, well, not problem, the trade-off with strong scaling in this case is that you get to be more accurate, right? Because you exchange gradients more frequently. The batch size is small, right, for everyone. But also you have less compute to do because batch size is small. Computation is proportional to number of samples. So eventually you start spending more and more time on the synchronization between these nodes. So you get classical Amdahl's law problem. Now your bottleneck is communications. So of course people try to stick with strong scale as much as they can because strong scaling gives you faster convergence, right? Less error rates, faster convergence, but you have to pay with a communication time. And in the early days, all you had here would be the pattern called O-reduce. O-reduce means everybody has to get the same average of all the gradients across everybody. And O-reduce bandwidth-wise, as I said, is proportional to the number of weights multiplied by the size of gradient. But luckily, you don't have to burst it all at once. You can proceed sequentially and stage it out, and it will be really nice and clean. And if you overlap, your I/O time now overlaps compute time, so it doesn't get as bad. But at some point, you have to go. You really want to get more compute, right? Because the whole idea of parallelization is like, well, I get more GPUs, more compute power, they compute things faster. But to mask that I/O overhead, you have to increase batch size per GPU. You have to send more and more samples per GPU, so they spend more time in computations. But that also means your conversion gets slightly affected because your error rate gets higher before you exchange the weights, not weights, so gradients. I think this even says here in the red text, accuracy gets worse if your batch size increase. And there is some empirical laws that connect batch size and convergence, but usually people get it from experience. I also want to make one other comment because I like history. Before things were run on GPU, I think seminal paper from Google from Jeff Dean was showing asynchronous distributed training on CPUs. Because back when people were like, well, GPUs are hard, CPUs are abundant in cloud, so they just use CPUs. And back then they did not use this synchronous training, right? Back when it was using parameter server, where you store the model weights, the shared model weights in one parameter server, like one, say, CPU machine or DRAM, and every worker has its own replica, calculates its batch, but updates weights globally, and all of them synchronized to the same set of weights. And they don't have to be synchronous, right? Here, you see, you have to do backward passes. In the end, you exchange everything in a log steps. So the benefit is that everybody gets on the same state. So by the end of backward pass, all the GPUs are on the same page. They have the same exact replicas. In a old school Google-style asynchronous training, it was like a bit divergent across the elements. The good news for backbone was you could add more workers to that pool or have redundancy easily, right? Because they all just exchange things asynchronously through central parameter server. The bad news was it wasn't very fast because it was CPU based, right? And it was also asynchronous, which meant your error would accumulate much faster and you converge much slower. But anyways, this, I hope, closes at least some page on pure data parallelism. So let's go to the next page. I can't remember, I think, if pipeline was at the time people did data parallelism. They were also like, trying to scale batch size per GPU is painful because convergence gets worse. right? So like, what if we instead try to parallelize by splitting the model across multiple GPUs? Like cool idea, because eventually all these methods to parallelize come down to you either split data across more GPUs or you split the model across more GPUs. It's a very unscientific and simplified way, but it captures the pattern, right? You have to somehow take this network structure, you either replicate it or you shard it across the GPUs. So pipeline was one of the probably early prominent attempts to, not attempts, successful attempts to parallelize execution of a model across main GPUs. It had another factor, right? At the same time, there was a different tension. Like a big model would not fit on one GPU. So it's different problem parallelization. It's just purely saying, like I cannot fit, I don't know how many billions of weights on a GPU HBM memory. Because back when you say have Kepler or something like this, older GPUs, smaller memories. And people had a simple trick. Oh, it sounds simple in theory. It's much harder in practice. You take network layers, right? They have multiple layers, and you just cut them vertically and put layers on different GPUs, like you see here, right? 3 layers, 3 GPUs. And when you do forward pass, you pass the activations, not gradients, through this chain of GPUs, right? And then you get a pipeline structure, which has natural bubbles, and you have to fill them up with mini batches, micro batches to keep feeding this pipeline. Because once you proceed through with GPUs, you have to go backwards and apply backpropagation of a micro batch. So that created an interesting pipeline structure, but you have to keep loaded, right? Because you start empty. Like from a Cray days, right? People like always been like pipelines are a way to parallelize things, but they have one bad aspect. You have to fill the pipe and drain the pipe, right? So in between you're great, but when you fill the pipe or drain it, it gets pretty painful and inefficient. So you create specific batching schedules. So you utilize that efficiently. And pipeline could be like long or short. People try to keep it shorter for efficiency. I mean, like you split this as much as necessary, pretty much, for pipeline. If you look at Llama paper, I think Llama 3.1, they have a pipeline depth of 4, if I'm mistaken. Maybe I'm confusing it. But I think people tried going that usually up to 16 pipeline stages, right? If you take a transformer which has 128 layers and you have 16 pipeline stages, you get what? You get 8 layers per stage, right? And I want to mention, like Jeff's slide says, it was done to fit the model, but it also creates a dimension of parallelism, right, as well. But the unfortunate thing, you have to modify the model, split it into multiple layers, so it gets hard to maintain. So people really, many folks I used to work with before didn't like pipeline parallelism, unless necessarily we try to avoid it because it was hard to like adjust the model. Unlike data parallelism was always nice. Model was the same, you just like split the data. Okay, so now we have 2 things, right? You can combine them too, right? You can say, I have, let's say, 2 replicas, and each one is a pipeline. And say each pipe depth is 4. So you have 2x4 parallelism now, data and pipeline, which already gives you twice more GPUs, right, than like just pipeline. So the whole idea of parallelism is like find ways to feed in more GPUs into that decomposition of the dimensions. And by the way, I think terminology is a bit confusing. Like people often say data parallelism and model parallelism. And when model is being split into like pipeline, tensor, expert, and so on. So pipeline conceptually is a variant of model parallelism, right? But very often people say model parallelism, and they mean the next slide. Let's see the next slide. I think it was called tensor parallelism, right? They always, it's actually tensor parallelism is a form of model parallel execution. So this one is more convoluted because it's conceptually it's straightforward. Remember, like you take what is it? It doesn't show the network here, the neural network. So you take the neural network, right? In the pipeline, you slice it vertically, right, across the layers. So layers are on different GPUs. In Tensor, you slice horizontally, right? And then every horizontal slice goes to different GPU. And so the idea was that you kind of have full stretch of a model, but only a part of it on one GPU. And when you do forward pass or backward pass, to do multiplications, you have to gather the weights from different GPUs. And every GPU does its own multiplication, and then we do some form of synchronization. Like here, what Jeff has, you have all gather, which is, I think, you do split n matrix splitting, because you have to split both activations coming to this network and the weights of a network as you proceed through. But here the idea was that if you slice a matrix in these sub blocks, your compute gets slower, compute demand, right? Matrices are smaller, but you also get higher memory bandwidth, right? Because you have to extract less weights from memory, and now your memory bandwidth efficiency is higher, right? I didn't mention it, but in general, in ML, memory bandwidth, memory wall is one of the most prominent challenges. Eventually, you cannot feed compute engines fast enough to do multiplications. So tensor parallelism is one way to alleviate this pressure, right? You have now more GPUs, right, to split the model across and do computations independently and then synchronize it. So you get higher efficient memory bandwidth per GPU. And so here you can see what we have so what is, I think B here means tensor slices, right? And A probably means activations, I imagine here. I'm not so sure about this slide, but the idea is generally conceptually similar. You have different portions of transformer network, right? Like you may have this FC layer, feed-forward layer, right? Fully connected MLP, and it has two big layers, FC1 and FC2 typically, right? Each one is a gigantic matrix to do multiplications, and you slice it horizontally into these subcuts of a matrix and put them in different GPUs, and then give everyone either partial activation or full activation data. And then the multiplications on every GPU, and then you combine them together to pass to the next stage. And typically, this operation is very traffic heavy, right? Because you have to pass across weights and activations. And there are different types of splitting either weights or activations to minimize either traffic volume or computation, right? Many types. There's like a classical 1D tensor parallelism. There's a 2D tensor parallelism, which is often known as tensor and context parallelism, where you split matrices for the weights and the activations across the GPUs. You can look at Llama 3.1 paper, which describes this exact schedule. It's pretty common method to train things. There's also more advanced methods coming from the 90s or 80s, which is called not 3D parallelism, but 3D slicing. So you can slice matrices across like 3 dimensions, right? Sometimes to make it even more efficient. This actually came from HPC land. People wrote linear algebra implementations like in the 80s and 90s, and they had to learn how to multiply matrices on the compute engines in distributed fashion. Because remember, like all computation during training is effectively a lot of matmols and other things. Some would say just matmols, but also nonlinearities, Swiglu, and other things which happen in, of course, there, and attention, of course, which has projections and other things. But that was, I think we just covered 3 things: data parallel, easy, simple to reason about; pipeline, people can visualize; tensor parallelism, it's like you'll get a bit more, worky about it because there's too many variants there, and it gets a bit headachy to reason about. But this slide says, what if you combine all these 3 types together, right? And the reason to combine is as I mentioned before, is twofold. One was to fit model in memory, right? So people often do tensor, not often, wrong word. Initially, people did tensor parallelism to fit in memory, right? And get some parallelism, extra GPUs. Tensor parallelism was done for both reasons, also fit the model and get more GPUs. I think getting more GPUs is more important because of parallelism. And finally, data parallelism is always there. You have so much samples, like let's say Llama 3.1 used 16 trillion tokens, right? So it gives you enough data to split across the GPUs and feed them. But if you put this in a schedule, right, in a three-dimensional decomposition, it shows you how would you split the model across GPUs, right? And how do you split the data across GPUs? Like here you have, what do we have here? We have, if you look at this one slice on the left, vertical and go in third dimension in pipeline. This is how we split the model. Like you have is, how many have here, Jeff? 1, 2, 3, 4, 5, 6, 8. 8 and probably, let's say 64 GPUs, which form a model parallel shard, right? Pipeline and tensor. And that's one shard where you split the model across. And then you replicate these shards across horizontal dimension, data parallel. And when you do the training, you split the data and feed into all these shards at once, right? They all get their own batch, do forward pass, pipeline fill, pipeline drain, and then gradient exchange in the end. But you exchange gradients across all these vertical slices in the end, in one pass. So one pass is done. You finish like one big batch, you get to the next batch, and until you exhaust every batch you have in the corpus. And typically it takes weeks, if not months, to complete full pass over all the data, single pass. That result is throughput, right? You get to use all the GPUs. Usually, of course, you underutilize compute cores because of all the overhead. Most of the overhead is communication and memory, right? Access. You have to pull the weights, do multiplications, synchronize all the data. So you usually never get to utilize GPUs 100% of their compute. I think the good utilization, people kill me for saying utilization because there's so many metrics to think about utilization, but typically you utilize around the GPU compute cores by maybe 30%, 40% if you're really lucky, right? If you ever can get to 80%, you probably get Nobel Prize or something. But that's, it's essential trade-off of parallel execution. You get more because you have more GPUs, but you also eventually underutilize each one of them because it's impossible to keep them all busy because of distributed nature of execution.
So I think that's an amazing introduction to parallelism. I think we should bring it closer to our podcast, networking.
Oh, shoot. I forgot. Yeah. I think you asked me to mention the traffic patterns at some point.
Yeah. What we have shown here is that different parallel dimensions are grouped in different ways. And they have different patterns. And as we discussed before, there are mainly two networks, scale up and scale out. Scale up is the network between GPUs that's usually much faster than outside network that allows very, very fast communication between GPUs in the domain of the network. We call it NVLink domain in NVIDIA. And then there is scale out network that is InfiniBand or IP network, IP Ethernet, that could be used for communication across all the GPUs in the group. And again, I'll pass it to Peter to describe the differences and which parallelism uses what network and for what reasons.
Yeah, so boys, I just got some ping from real life. Not sure if I need to attend to it or not. Give me a second. So I guess what I want to just capture, because I'm not sure how much time I have left right now. But anyways, look at this picture. So every slice, vertical slice, right, is a model parallel. When you do tensor parallel execution, your traffic pattern will be all gather, reduce, scatter, right? I don't think we have time discussing it, but this is how it usually works. You do matrix multiplications, you synchronize the weights using all gather, reduce, scatter, right? When you do pipeline, you go through and you feed the point-to-point messages in a sequence, right? You go like one after another in a sequence. So as you go to that dimension, third dimension, you have a send receive across each of the tensor slices. So it's actually a very benign traffic pattern. The tensor parallel is most intense, all gather, and reduce, scatter. And then as you go data parallel, it's all gather, reduce, scatter, which is much, much smaller because you only have to exchange the gradients once, right? So most intense here is tensor parallelism, which goes across vertical dimension. When pipeline is pretty straightforward, it's like activation passes. But then going horizontally, you have data parallel or reduce, all-gather, reduce, scatter. So guys, I might need to step out. I really apologize. Just something came up in the real world. So I try to wrap up in a second, but I think this captures the whole idea of parallel traffic. But in my case, real life has intervened.
Okay. Thank
Okay.
you.
I really apologize. I guess Jeff can continue on network effects. And I think if we give opportunities to talk about parallelism at a high level, I apologize for any inaccuracies because people might just kill me for being so high level about those things. But I hope we at least captured the essence of parallel decomposition of the DL models.
It was great coverage. Yeah, thank you, Peter. This is great coverage, and speaking for myself, I think I'm going to have to rewatch this show about 3 times. Really
no worries. Thanks for having me, guys. And apologies for the short notice. I just need to step out. Thank you.
No problem.
Thanks again for having me.
So to kind of finalize this picture, if you look at the numbers, tensor parallelism is on a single node of 8 GPUs. The numbers are not by surprise, those numbers. In current generation of GPU servers, usually you would see 8 GPUs on a single server. But it also means that you've got inside what we call scale-up network that is in current generation of servers almost 10 times faster than outside network to exchange the information. So tensor parallelism, due to very high bandwidth and extreme sensitivity for latency, is on the same server. So 8 GPUs in this case really mean same server, right? So you can use this very, very fast network with direct access to memory and across all the GPUs to use tensor parallelism. So pipeline parallelism allows us to scale horizontally to more nodes. And then if we look at data parallelism, because it's more effective, it's less data in general to exchange and less often, you can see that this is where you scale to this thousands, potentially tens of thousands of GPUs in the network. So those are different dimensions, and all these patterns have very different requirements with regards to network. So they all share same property of being completely lossless. It's a memory transaction. Remember, it's RDMA. You read and write memory buffers. You lose the packet, don't. But from latency perspective, from burstiness of the traffic, they are very different, and that's why you see 3D picture that uses different composition to provide these very, very large clusters. Right, at this point, I'll stop sharing. Where are we? Robert, could you please take slides off so I can stop sharing? Can you hear me?
Yes.
Yeah.
Please set them down.
Yeah. So we are not sharing anymore, right?
Right.
Good. For whatever reason, I don't see the screen. I see it now. So unfortunately, Peter has to leave for some real life event.
Real life customers are always interfering with fun stuff.
So what we try to do here is to introduce you to kind of basic building blocks of AI training and driven by the communication library patterns and how they result in different traffic flows across the network. But again, they all share very important property. Network must not come in the way. If it does, you are losing GPU time. You are losing your time to train the model. Potentially, if your network is, and there are failures in the network, right? If your failure is severe enough or doesn't converge fast enough, eventually you'll restart the job. What does it mean to restart the job? You do snapshots. It depends how often you do it and it's a whole topic for another discussion. Practically, if your job fails, you go back to last snapshot that could have been taken 1 minute ago, but could have been taken 24 hours ago. You load latest information and you restart whole job. The snapshotting has some interesting properties, whether it's synchronous or asynchronous. If snapshotting is synchronous, GPU stops doing its work while you do snapshots. That's why snapshotting on itself it's a very interesting area, because the more often you do snapshots, the more time you lose, right? So there's a whole discussion about how you do snapshotting. Practically, if job fails, you roll back to late known information. So you lose the time that you spent on training between last snapshot and time of the failure. So it's very important to have your network stable to begin with. And again, there are going to be failures. We are talking about networks with millions of links.
Sure.
So you need to know how to react on failure, how to converge. Again, we go back to basic networking. Build your network in a way that it can converge on as fastest. Aggregate, reduce amount of state, reduce possibility for the loop. So all the stuff we'll have to discuss with Ross White and other routing people, right? Dimensions are important. So we said the amount of traffic, a GPU can generate 400 gig single flow live rate. So if you under-dimension or trying to save money on, oversubscribing in wrong place, you'll pay twice. So there's a very good proverb saying that greedy person is paying twice. That's exactly. If you're not paying twice, you're probably paying 10 times what it should have been. So position and dimension your network correctly. Don't try to save on less bits. If anything, you want to be your network faster than your compute. Right, and given the size of the cluster, keep basic hygiene. Make sure you document everything. Make sure your addressing makes sense. Make sure that when you look at IP address, you actually understand where it came from. Because again, you end up having 10,000 IP addresses. It's very good to have proper DNS in place, proper IPAM in place, just to figure out that this address belongs to a particular part of the cluster. So you don't spend 30 minutes on figuring out where it came from. And back to BGP, make sure there's no path hunting, that you use proper SN allocation scheme, that your IP scheme is allowed for aggregation. All the stuff that's not really related to AI, it's just how you do networking properly. Right. It's just now cost of bit lost or bad design is order of magnitude, so good enough for you to lose your job, pretty much. So that was my message, pretty much.
Okay, cool. Well, Jeff, I appreciate the wrap up on that, and I think with that, having lost our host here, but we were pretty much, I think we pretty much got to the end of it anyway. I guess we'll wrap it up here and start again in 2 weeks, right?
Yeah, and so we've got a couple of interesting ideas for upcoming shows. I think we still want to bring a couple of people from the industry to talk about their deployments, so potentially some other hyperscalers, if we can make them available. And I think we have some pretty good ideas for what's next in terms of, if it's not BGP.
Yeah. Do you want to the one person we were discussing from Alibaba? Do you want to pursue him?
Yes, I'll talk to Eddie. Eddie is now in Asia, to my knowledge. So at the time he comes back, I'll talk to him. And
okay, wonderful.
There's the white paper published by Alibaba. It's public for SIGCOMM called HPN, which is the AI cluster Ali built. Amazing paper, very readable, very accessible. Talks about how you work on resiliency issues and stuff that we discussed here. So, and I'll try to get person from Alibaba to join us.
Great. Okay, and with that, I will say thanks to everybody for joining us, and we will see you again at the next Between Two Nerds.
Yep. Bye, everyone. Bye, Jeff. Thanks, Robert.
Bye, Jeff.